All right, so we're continuing to talk about intermolecular interactions. And so let's review what some of the, let's review what the objectives are for this segment. So if you recall, we're going to be describing the main types of intermolecular interactions. And we got through a lot of them, dipole-dipole interactions, ion-dipole interactions, and recognizing which molecular interactions are present given a molecular structure. So we've got a good sense of how to do that, and looking for polarity, looking for obviously total charge if it's an ion, and looking for hydrogen bonding. And be able to predict the rankings of physical properties based on strengths of interactions with molecules. We'll get to that soon. So let's actually review a little and predict some rankings of physical properties based on strengths of interactions of the molecule. Very important type of interaction. It's weak, but occurs everywhere, even for nonpolar molecules, so it becomes pretty important. So these are London dispersion forces. And what they are is essentially induced dipole interaction. So let's just say you have two molecules that are not polar. Here we've got our two molecules that are not polar there, but there's going to be some fluctuations, right? Heisenberg uncertainty principle. There's fluctuations in the environment, and when that happens, you get a certain time you get some positive interactions on one side of the molecule. You get, as the electrons are sloshing around, you'll instantaneously have less electrons on one side and more on the other. But when you do that, you've created a dipole, and when that happens, then you induce a dipole in the next molecule over, right? Its electrons will slosh around so that it has more electrons lined up with the positive end of the other dipole. And so as you have a bunch of molecules that are around and all the electrons are sloshing around, they're going to slosh around such that they tend to get these momentary dipoles aligned with each other more times than not. So these are called London dispersion forces, or induced dipole interactions. And the key thing here is the more electrons, the more dispersions. If you have something like benzene that has pi electrons, remember it has those p electrons in the pi orbitals that are all sloshing around, so they can move very easily from one side of the molecule to the next. So you got a lot of interactions there. Larger alkanes like diesel, remember diesel fuel, you might know has problems in the winter. If it gets too cold, it freezes, because those are diesel fuel has larger alkanes than a normal gasoline, and therefore larger dispersion and attendance, more interactions, and will have higher boiling points. Okay, so that's the idea behind London dispersion interactions, and they occur everywhere. Remember, we saw let's look at some cases of alkanes. So we'll look at the melting and boiling points of N-alkanes. So N-alkane, it means normal alkane. It just means an alkane is basically carbons and hydrogens. So it's a hydrocarbon. And N-alkane is you just keep connecting the carbons in a line, and then the hydrogens stick off of that. That's a normal alkane. So it's just a linear carbon with hydrogen sticking off of it. And as you can see, as you go up from CH4, the methane, the smallest alkane, all the way to C16H34, the melting points go up, and the boiling points go up as well. They all go up because the bigger it gets, the more interactions it has. So molecular weight, like the total number of electrons, is the biggest effect. There are some other minor effects as well. Like, for example, if you look at a more branched C16H32, where the carbons are, you have more carbon-carbon bonds, then you can see that you get a little bit lower melting points and lower boiling points. And that's because they can't pack together as easily. There's less surface area, and so there's less surface area for these dispersion interactions to occur upon. You get some other weird effects like neopentane, C5H12, that's like very symmetrical. And so it has less surface area to pack, so its boiling point is lower. Its melting point is actually higher, and that's just because it packs so nicely. It's this like nice, almost spherical thing. It packs super well together. And so it's in a solid, it's easy for getting everything very closely packed, and its melting point is actually higher. Whereas if you look at normal C5H12, and those are just right along the lines. Benzene is another example that's a little bit different. Its boiling point is higher because those p electrons are very easy to move around, and you get, they easily create induced dipoles, and there's some other weird quantum effects as well. But it's not that big an effect, right? It mostly follows the trend line of molecular size. The melting point is also pretty high because it's really easy to stack together because it's nice and symmetrical. You can stack these things on top of each other, very space saving. Yeah. So, but as you can see that the dominant trend is still just the size, especially for the boiling points. Freezing points depend even more upon shape, freezing, melting, but the boiling points, it's mostly just the size with some other weird shape effects mixed in. But the overall trend is simply the bigger it is, the bigger the London dispersion forces. All of them are based on electrical charges. We get opposite charges attracting, and that's why we get the interaction. So the strongest, ion-ion interactions within ionic solids, bigger than 100 kilojoules per mole. Ion dipole are sort of in the 100 kilojoules per mole range, occur between ions and polar solvents, sodium dissolved in H2O. Hydrogen bonding occurs between polar H and lone pair on highly electronegative atom, NH3, H2O, alcohols, and those are like in the range of 10 to 40 kilojoules per mole. Normal dipole-dipole interactions occurs between molecules with large dipoles. Dipole-induced dipoles and London dispersion forces are weaker. They occur for all molecules, more prominently for easily polarized molecules. Easily polarized molecules will be ones that have a lot of electrons sloshing around. All of these are electrostatically charged based, but depending on how the electrons stick to their molecules, you get different behaviors. Oh yeah, induced dipole, sorry, I didn't go all the way down. Induced dipole, those are the weakest London dispersion forces. Okay. So there's one other interaction that I think is useful to talk about that you hear a lot about, but is really just these other interactions in disguise. You might have heard of the hydrophobic interaction, right? How come water and oil don't mix? And the reason is there's no special interaction here. It's just a combination of the other interactions. So H2O has hydrogen bonding, which is strong, right? Okay. Here I've got cyclohexane, London dispersions, which are weak. So you might think, okay, those are weak. Well, what about the water cyclohexane interactions? Those must be even weaker, right? Because these things don't mix at all. But that's not true. Water and cyclohexane has dipole-induced dipole interactions, which are stronger than the induced dipole interactions between. So water oil is actually stronger than oil. Oil, they're not very strongly attracted to each other, but water oil, because it's dipole-induced dipole. But the total energy of the fluid is minimized with lots and lots of water-water interactions and less water-oil interactions. So really, the oil really wants the water, but the oil is left lonely and alone. So it's not that oil and water don't interact with each other. Oil loves water, but water loves itself more. So the oil is left alone. And that's the reason for the hydrophobic interaction. It's not any new interaction. It's just the combination and mixtures of these other intermolecular interactions that we've been talking about. Why are we learning all these about intermolecular forces? It really comes down to the consequences. Stronger intermolecular interactions mean for liquids, higher boiling points, larger enthalpies of vaporization, greater surface tension, greater viscosity, and for solids, a higher melting point, a larger enthalpy of fusion. And we'll be talking about these quantities, boiling points, enthalpies of vaporization, all these much more when we talk more about phases and understanding phase diagrams and transitions